Okay, everybody, this is 13.2, day 2. We're still analyzing data and looking at different ways we can interpret information that we have. So today, the essential questions we're going to be looking at is talking about box and whisker plots. When is that helpful? And then normally distributed data. So these last 2 bullet points here. So we're going to talk about those last 2 sections. So we're going to think through what are some different ways we can talk about other than standard deviation and mean, median, and mode. What are some other ways to represent and talk about data? So first order of business is box and whisker plots. So you guys made these before. We're going to be using our graphing calculator as well, so make sure you have that handy. Basically, what you're looking at when you do a box and whisker plot is breaking a set of data into quarters. So those are called quartiles. So if you take all of your data and divide it into 4 equal chunks, that's called a quartile, or breaking it into quarters. So quartiles. So 25% of each part of the data is distributed. So you're looking at for where all those 25% are located. So what we're going to do is we're going to talk about how do you organize that? How do you break data into quarters? Well, you start with a median, so that's the middle number, we know that, and then you find what's called the lower quartile, so the median's the middle. The lower quartile is the middle of the bottom half of the numbers, and then the upper quartile is the middle of the top half of the numbers. So if you think about breaking your data set into 4 equal chunks, you'd find the middle first, and then the middle of the bottom, and the middle of the top. So the lower quartile, or what we call our Q1, is the median, so the middle number of the bottom half of the data, so of the numbers before the median. So I'm just going to say before M, so M is the median. And the upper quartile, which we call Q3, the third quartile or the third quarter, is the median of the numbers after N. So the median of the numbers after M. So it's kind of thinking about breaking the top and the bottom half into halves again and finding that middle. So the interquartile range then is the distance between those 2 quartiles. So it's the difference. We're going to be using that to calculate something else here. So that's why we're talking about it. So it's the difference of the lower and the upper quartiles. Oops, see if I can write that better. So the upper and the lower quartiles. All right, so what that means is if we want to think of it more as like a formula, they call the interquartile range, so the IQR would be equal to the Q3 minus the Q1. So finding out how long basically the box is when we represent that in a box and whisker. So this is really seeing how the data is dispersed. How close is it together? How far is it spread apart? And it's a really nice way to be able to see that when we look at those 25%. If something's really far above or below a data set, I know you've talked about this before as well, that data point is called an outlier. So we're going to talk about how you calculate that, and that's why we need that IQR. So if we're going to actually have an outlier, the mathematical definition is 1.5 times the IQR, either above the third quartile, so above Q3, or 1.5 times the IQR below the Q1, so below that first quartile. So if something's mathematically that far away, it's actually considered an outlier. I know we could just kind of eyeball a data set and say, wow, that one looks really big. Doesn't look like it fits with the rest of the pattern, but that's actually how you mathematically calculate it. So just to make sure we understand what that's going to look like. So we're going to talk about how do we represent this set of values visually. So those quartiles are represented in a graph by a box and whisker plot. So that's what we're going to use to represent that. So this is represented by a box and whisker, kind of a fun name because it kind of looks like a box with little whiskers sticking out of the ends, which is kind of a little bit creepy actually when you think about it, but that's okay. It's a box and whisker plot, which uses those 5 numbers. The 5 numbers are the minimum of the data set. So like what is the smallest actual value in my data set? The lower quartile, so the Q1, the median, that middle score, then the upper quartile or the Q3, and then finally your maximum value, whatever the highest actual number is in your data set. And remember the maximums and the minimums, those could be outliers potentially. So these numbers are called the 5-number summary of the data set, not so critically important that you remember that name of it, so the 5-number summary, but those are the 5 numbers that we would use to represent a data set with a box and whisker. So I just want to show you an example of what I'm talking about. So if you can just kind of make a picture here with me. So we use a number line. So this is a traditional number line. So it goes numerically in order, proportional, all that good stuff. The box then is representing that IQR. So this bottom of the box and the upper part of the box, that's your Q1 and that's your Q3. The median is wherever that point is in the box. So it's usually wherever that line is going to be. So we'll just label one. I'm just kind of making up an example here. So the median shows the middle of the data set. And then we have our minimum value, whatever that minimum value is in your data set, the actual smallest, and then we have the maximum value. Now, if it's an outlier, it wouldn't be connected to the whisker. So if there was actually like a maximum that was an outlier, it would just be a dot out here. It wouldn't be connected to the actual whisker, and we'll talk about how to draw those as well. So box and whiskers, again, it's on a regular number line, going up at regular intervals, but we show where each of the data sets are. So 25% of your data set is found between the minimum and Q1. 25% is found between the Q1 and the median. 25 here as well, and then 25% here. So you can get an idea of how distributed the data is. So in this case, this is much more closely distributed because that 25% is much shorter than, say, the upper part of the box, which is more spread out. So the scores are clustered closer together. 50% of your data is always found within that box. So 50% is on either side of that median between the quarters. All right, so let's try an example just so you can see what box and whisker looks like. So to make a box and whisker plot, the most important thing is to get your data set in order, being able to put those numbers in order. So that's kind of our first order of business. Bad puns even on the videos. All right, so it starts with, and we're just going to kind of go ahead and reorder, 12, and then kind of just keep track of what you have here. Then there's a 13. Go ahead and reorder, and then pause the video so you can do that, and then we'll talk about how to break it down. All right, so hopefully you have yours in order as well. So what we need to do first is find the median, the middle score. So I know a lot of people kind of use the go back and forth strategy here to see if we can find the middle. Also helpful to know how many numbers are in your data set. So in this case, we have an even number of data values. So there isn't actually a true middle score. So in that situation, the median is going to be right here, right in between. So we actually have to average those middle two numbers. So in this case, we'd be averaging the 18 and the 20. So our median would be a 19. So it is possible that the median isn't actually a value in your data set, but that's where the middle would be. All right, now to find the quartiles, we're going to take a look at the bottom half of the data, and we are going to find the middle of that as well. So some people, again, kind of employ the, let's see where that middle number is. So in this case, again, there's no true middle. So I'm going to go ahead and average those two data values to find my Q1. So my first quartile would be at 15. And then in the second half of the data, so the 50% of the data that's above, again, I don't have a true middle, so I'm going to average those two. So the 24 and the 26. So my third quartile would be the 25. So we can find those numbers pretty easily. So in my 5-number summary, my minimum of my data set, that's the 12. My Q1 is 15. My median is 19. And then I have a Q3 at 25, and my maximum value is the 42. So those are the 5 numbers. So if I'm going to make my box and whisker, I'm going to need to figure out if I have any outliers. So before I actually do the box and see if it's connected or not, I'm going to calculate the outliers. To find if something is an outlier, mathematically, I do 1.5 times the IQR, and I'm going to add that to the Q3, and I'm going to subtract it from the Q1 and see if that is truly an outlier. So I need to calculate my IQR, the length of the box. So that's the difference between the Q3 and the Q1. So that's my 25 minus 15. So the length of my box is 10 units long. So that means 1.5 times my IQR is going to be 15. So what that means is if a data point is more than 15 above the third quartile or more than 4 or 15 below the first quartile, then it's going to be an outlier. So let's check for the upper one first. So if I take my 1.5 times the IQR, my 15, and I add it to the Q3, so 15 plus 25, that would put me at 40. So that means if I have a data value that's more than 40 away from, or more than 40 in my data set, then that's going to be an outlier. Well, I have a 42 in my data set, which tells me then, oh, this guy is going to be an outlier. It's more than 1.5 times the IQR above that Q3. So anything bigger than 40 would have been an outlier. So let's go the other direction. What about 1.5 times the IQR below Q1? So I'm going to do Q1 minus that value. So I'm going to do, what was my Q1 here? Looks like Q1 was 15 minus that 10, and that would put me at 5. So if I have any data values that are less than 5 in my data set, it would be an outlier. Well, my lowest number is at 12, so I don't have any outliers on that end. So the only outlier that I have is the 42. So I actually can technically calculate what that looks like for an outlier. All right, so let's go ahead and make this box and whiskers. So see if we can draw this graph. So what I'm going to ask that you do for these always is give yourself a number line. So I'm going to make a nice number line here. So something that I have to easily be able to do this. My smallest number is 12 and my biggest number is 42. So what I want to try to do is come up with regular intervals here so I can represent that. So you're going to have to decide what works best for you. So I'm going to start at 12, and I think I'm probably going to go by, I don't know, go by at least 2s. So 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. And then I have to go a little bit further here to get to my 42. Now I didn't label all of them here, so I could go back a little further and start at 10. If you want to label everything, go ahead. We just need to make sure we're going at regular intervals. We want this to be proportional. So I have my number line now. I'm going to represent all these values. So my smallest number, my minimum, was at 12. So I'm going to represent that on the data set by the end of the whisker. My Q1 is the bottom of the box. That happened at 15. So this would be 12. This would be 16. So 15 would be right in between there. So that's the end of my box. The whisker is going to connect to that. The top of my box is going to be at the third quartile, which is 25. So 22, 24, 26, so I'd be halfway in there. So I have my box. All right, the middle, the median, the middle score was 19, which would be right here. So there's my median. That's where the line goes in the box. My outlier is at 42, so I'm going to go ahead and put that there. That's not connected to the whisker. The first data value that's not above 40 would be my end of my whisker. So that data value looks like was 27. So that's where my end of my whisker is going to be. So 27, this would be 28, so 27 be about there. And I can connect that. So I have my minimum, my Q1, my median, my Q3, and then I have my maximum value out here, which also happens to be an outlier. So that's a box and whisker plot. So it's nice to be able to see that distribution. So obviously, the smallest, or maybe not as obvious, but 25% of our data is here, 25 is here, 25 is here, and 25 is all of this up here. So the top is much more dispersed, spread out than the bottom was. All right, if you grab your graphing calculator, I just want to show you something. If you take a moment and go ahead and pause the video and go into Stat, Edit, and enter in this data set, does not have to be in numerical order. You can actually make this graph. So go ahead, pause the video, get your data in there in your list 1, and then I'll show you how to do that calculation. So be able to make the box and whisker. So once you get your data in there, you're going to go to Stat Plot, and you're going to turn Plot 1 on. And we want a box and whisker. So if you look at the different types, we want the one that shows with the outliers. So I'm going to choose the one, and I know that it has outliers, so I'm choosing that one. Your X's are in list 1. Everything's all set, ready to go. You want to make sure that nothing else is in your Y equals, so you don't get any random line going through. And then the quickest way to do this is zoom stat. So you're putting in something in your stats menu, so number 9, do a zoom stat, and it's super cool. You get that box and whisker that we just made, which looks awesome. Now, another cool thing, if you press trace when you're on your box and whisker, look at what happens. It gives you the numbers down at the bottom. Your median is 19. If you just arrow, there's your Q3, 25. There's your top of your whisker. There's your outlier at 42, and you can go back and get your Q1 and your minimum. Super awesome. So this is a great tool. The other thing you can do is you can go into your stat menu and over to calculate. So if you don't want to have to organize this data yourself and figure out where all those middles at the top and bottom, remember we can go to our one variable stats and go to calculate. This is with the data in your list, and you get X bar the average, you get the number of terms, which was 12, with the number of data sets. But look at the bottom, you get the minimum is 12, Q1 is 15, you just have to arrow down, median is 19, Q3 is 25. Max is 42. You get all those values as well. So your graphing calculator can be a great tool. We need to understand how it works by hand as well, but this is a great option for you. All right, let's talk about our last piece of info here. We're going to talk about normal distribution. So a normal distribution is looking at large data sets. And in a large data set, what normally happens, hence the name normal distribution, is that the data will follow this, what they call a bell-shaped curve. So it makes that sort of a shape, that most of the people or data values are going to be around the average, and the further that you get away from the average, the fewer data sets there are. So you get this idea, or this shape, this idea of a bell-shaped curve. So down at the bottom here, I'm just going to draw what I mean. So we have a picture that looks something like this, where the highest point, and then this curve, the blue curve, represents the number of data values at that point, so that's the distribution, is occurring at the average. And then the further you get away from the average, we have fewer and fewer scores. The further away from the average below, we get further and further scores. Like, think of like average height. Most people are going to be around average height. The taller you get, the less people there's going to be. The shorter you get, the less people there are going to be. There's just not as many in that data set. Or grades as well. If you look at the number of people at the average, that's where most of the scores were. But the higher you go, like think ACT, very few people get that 36, but also not that many people get a 12 either. So very similar. Can you take a look at the 4 data points here? I have 4 bullet points. Go ahead and take a moment, pause if you need to. Here are 4 big properties that are always true when we talk about normal distribution. I know you guys talked about these before, but the total area under that curve is 1, represents 100% of the data. About 68% of the data lies within 1 standard deviation of the mean. 95% of the area lies within 2 standard deviations of the mean, and almost the entire data set, 99.7% of the area, lies within 3 standard deviations of the mean. So I want to be able to draw that and have you draw that as well. So you can make sure, pause, get those 3 pieces of information, but let's show that graphically. So I want you to see what that looks like. So this is what they're saying. So remember the average, so we can go ahead and draw this. Here's our average, or our median, our mean, I should say, X bar average. So 68% of the data lies within 1 standard deviation. So that's what this means. 1 below and 1 above. So adding whatever your sigma is and subtracting it. Then 95% of your data lies within 2 standard deviations, above or below. And then 99.7% lies within 3, adding 3 above or adding 3 below. And this is for really large data sets, so these distributions. If you want to look at it a little bit differently, thinking about the average in the middle and breaking it up on either side, we can just cut all of those in half. So if it's 68 across for 1 standard deviation, that means this way is 34 and that way is 34 to get the total. And same thing for the next ones. If the next one all the way out to 2 standard deviations was 95, I can break that up into 2 sides, and you actually get the amounts in each part, which is really handy. So I would also have this visual as well if you want to take a moment to jot that down to get the percentages. It's just a lot easier for our calculations if we have those. So take a moment and go ahead and pause if you need to. We're going to talk through a couple scenarios on normal distributions just to remember how they work when we're looking at probabilities. So how likely it is that our data value that we're looking at is actually in a particular part of that data set. All right, so let's take a look. You're going to need to add this example. I just put the picture here again so you can see it, so we can talk about it. This is just in general for any data set. We're going to look at a data point, a data value. So X is standing for a number. So say it's a height of someone, and we want to see how many heights are within whatever range. So what this inequality is saying, this is 1 standard deviation below, so X bar minus sigma, and this is 2 standard deviations above. So X bar plus 2 sigma. So it's meaning 1 below to 1 or to 2 above. So I'm going to go ahead and mark that on the picture, and you can do that on yours too if it helps. So from 1 standard deviation below to 2 standard deviations above. So graphically, visually, we're talking about any data point that lies within that part of the bell-shaped curve. All the x's that are in there. Well, let's see if we can figure out what percent would that be. If you randomly pick one value in your data set, what's the likelihood or probability that it would be in there? Well, that would be 34% from this one, 34% chance for that one, and another 13.5% chance for the last one. So we can just total those up to see what the likelihood is between each of those values. So we can get a total percentage. So you can do it in percent form or you can do it in decimal form. Just kind of depends on what version we'd like to say. But ultimately that would be 0.815 or an 81.5% chance that if we randomly pick a data point, it's going to be in that range. Okay, let's take a look at another one. So see if we can keep figuring out what these inequalities mean. X is your data value, so the data is less than 2 standard deviations below. So that's what that means, 2 standard deviations below, because it's subtracted, right? So what's the probability that's less than that? Well, that's not too much. Here's 2 standard deviations below. What's the probability that it is less than that? Well, there's a couple different ways we can figure that out. We can just add them up, which is kind of a nice way to do it. So what are the two places? It looks like there's a 2.35% chance. So you could say 0.0235 if you wanted to do that as a decimal. And this last little chunk, there's only 0.15% chance. So that's 0.0015. So if you wanted it a decimal, that's 0.025. As a percent, though, if you add these two numbers up, that would be 2.5%. There's only a 2.5% chance that you're going to be able to land in that smaller one. So if you're thinking about heights again, it's pretty unlikely that someone's going to be that much shorter than the average if you think about it in that way. All right, let's try one more to see if we can get the other end too, so we can get both perspectives here. So what is the probability that your data value, so your x, is greater than, this would mean 1 standard deviation above? So the number you pick, the height you pick, is 1 standard deviation or greater. All right, well, here's 1 standard deviation or greater. It would be all of those values. So we'd have a 13%, 13.5%. We're going to have that 2.35%, and then that 0.15%. So again, you can do it decimal or you can do it as percent. We would have 0.16 altogether, or that would be the same as 16% chance. So there's a 16% chance in that data set you choose a number that was there above. So just even being able to read the read the symbolism, I think is important when we talk about normal distributions. All right, so let's take a look at an actual example. So we were talking about heights, so we'll do that. So what if we look at the heights of a large sample of women normally distributed with an average of 64 inches and a standard deviation of 2. So here's what we're going to do. We're going to try to draw that normal distribution. So we're going to draw our normal distribution curve, which is representing 100% of the data. And I'm going to show my average or my mean in the middle, and that's at 64. So that's my average. The standard deviation is 2 inches. So as I mark on my number line, I'm going to be going by 2's then. So 2 inches above. So their height would be 66, and then that would be 1 standard deviation above. 2 standard deviations would be at 68, and then 3 standard deviations above would be at 70. I'm going to do the same thing going in the other direction. So 1 standard deviation below would be 62 inches tall. 2 standard deviations below would be 60 inches tall, and 3 standard deviations below would be 58. So just kind of getting that distribution set up so we can understand what's happening with it. So 1 standard deviation, so that's sigma, this is 2 sigma, and this is 3 sigma. And you can go the same in the other direction. And then we have 2 sigma, and then we have, 1 sigma. All right, so let's answer some questions. This is how our data set is distributed. So what percent of the women are between 66 and 68 inches? All right, so 66 or 60 and 68 inches. So 60 is right here, and 68 is right there. So that's 2 standard deviations below and 2 standard deviations above. So one way you can look at this is you could add up all 4 of those sections. Or if you know it's 2 above and 2 below, go back to my picture, 2 above and 2 below, that's just 95% of your data. So one way to look at it is just to think it's 2 above and below, so that'd be 95%. But we could also just add up each 4 of those sections. So I know it's a 13.5, and it's a 34, and it's a 34, and it's a 13.5. So we can put them all together too to get that same value. So we're using that same picture and those same percentages to be able to tell what we have for each one. So we have a 34 and a 34, a 13.5, and a 13.5. So it's a real nice way to be able to do that. But there's lots of different ways to think it through. Okay, let's try another one. About what percent of the women are at most, okay, keywords here, at most 60 inches? Well, what does at most mean? Well, it means that or smaller, right? It can't be any bigger than that. So that means your data value is less than or equal to 60 inches. All right, well, let's see what that means. That means we're starting here at most 60 and going this direction, right? We're going back. So at most, that would be those 2 pieces then, which was, if you remember on your picture, this is 2.35 and this is a 0.15. So the likelihood that it would happen would be just those 2 sections. So 2.35 plus our 0.15 would be 2.5%. So only 2.5% chance that you're actually going to be able to get that value. So we can definitely take a look at different ways to put them together, but I think being able to write, hey, what's the expression I'm looking for? Okay, let's try just a couple more, then we should be all set. What is the probability that a woman is in between 58 and 64 inches? So 58 and 64, so right here. All right, well, we can just total up those 3 sections. Looks like we have a 2.35, we have a 13.5, and we have a 34. So we're looking at the likelihood she would be in that height, and that looks like 49.85%. Okay, I'm curious if there's another way that we could have figured that out. Well, this is almost half the distribution, right? The only part that we're missing is that 0.15 down at the end. It's almost half of the distribution minus that. So couldn't we have done 50 and then minus the 0.15? And guess what? That gives you exactly the same answer. So kind of interesting. There's different ways to do this and look at it depending on how you see it. All right, so last one. Let's take a peek at this one. So what is the probability that a woman is at least 66 inches, at least? What does that mean? That means their height is either greater than or equal to 66. Okay, so we're talking about this then, that part of the graph. So again, we can add them up. So we got a 13.5, and then we'd have another 2.35, and then we'd have our 0.15. So we can just add them up and get that total. You could also think about doing some subtracting. So you can do your 50 minus, again, if that's easier. But ultimately, that's only a 16% shot, right? So we know that there's fewer people that are going to be that tall to be able to do that. So kind of cool, right? Be able to look at these different values that we have for normal distribution. So that is day 2 for our section 13.2. So we have box and whisker, and then we have our normal distributions.